Right, okay, so today we're going to be looking at reversible reactions. I would recommend that you follow in the textbook and also using the revision guide that I made for you with the mind maps on there. Before we carry on with this, make sure that you already know how to balance chemical equations, signs of chemical reactions, and what endothermic and exothermic reactions are. Okay, so in most reactions it's very difficult to go back to the starting materials, and so here are some examples of reactions like that. In some cases it's a little bit different, so as you can see in this one, when we shake up the bottle, a chemical reaction causes a colour change, it turns blue. Then if we leave it for a bit, we should start to see that the blue colour fades, and this is because this is a reversible reaction where the products can react back to form the reactants again. Okay, an important reaction like this that we should look at is the reaction to make ammonia. We use H2, hydrogen, react it with nitrogen gas, and they react together to form ammonia, which is NH3. So we'll quickly balance that equation. We need a 2 there and a 3 there. Right, the NH3, the ammonia, can also react to form hydrogen and nitrogen, and so it's a reversible reaction because the products can react back to form the reactants. In a closed system where nothing can enter or leave the reaction vessel, we develop what's called an equilibrium, and that's where the rates of the forward and back reactions are the same, as can be shown here by this demonstration with. So she's going to pour her reactants into his beaker, which is the forward reaction, and he's representing the back reaction, pouring his water into her beaker. And so as we can see, we've got forward and back reactions going, and at the end we still have the same amount of water in both beakers. So in our example of making ammonia, in our reaction vessel we'll have a mixture of H2 and N2, the reactants, and also NH3, which is our product. So at an equilibrium you always have a mixture of reactants and products. Okay, we can change the composition of our equilibrium by changing the conditions under which we do the reaction. So we can do a little table like this. We look at pressure. If we increase the pressure of our reaction, and we've got more moles of product when we look at our balanced equation, then what we do is we end up decreasing the yield. So we decrease the yield. Conversely, if we then decrease the pressure, we increase the yield. So we've got more moles of products, and we decrease the pressure. If we have a low pressure, then we get a high yield. Okay. Now if we look, we've got more moles of reactants than products, and we increase the pressure, then we should see an increase in yield. So we get a high yield at a high pressure. And conversely, if we decrease the pressure, then we get a low yield. Right, if we look at temperature then, the forward reaction is exothermic, and we increase the temperature, then we decrease the yield. Now, if we decrease the temperature, then we increase the yield. If the forward reaction is endothermic, then an increase in temperature increases the yield, and a decrease in temperature decreases the yield. Now, you probably want to get that table written down and memorised for the exam. So now we're going to look at how ammonia is made in industry. We use a process called the Haber process, where we collect nitrogen from the air, and hydrogen from natural gas, react them together to form ammonia. There's the balanced equation. We do this under the conditions of 200 atmospheres pressure, 450 degrees centigrade, and we use an ion catalyst. So if we look at the conditions they use, the pressure first of all, if we look back at the equation, we can clearly see that we have 4 moles of gas of reactants and only 2 moles of gas of products, if we look there. And so that means that we've got more moles of reactants. There are more moles of reactant. If we look back at our table, then that means that increasing the pressure will increase the yield of ammonia. However, we don't use too high pressure because a higher pressure is more expensive and it also makes the whole process more dangerous. Right, if we look at temperature then, a low temperature will mean a higher yield of ammonia, and that's because the forward reaction is exothermic. At low temperatures the rate is very low, and so 450 degrees is a compromise between the yield and the rate.